It's okay, I think you can.
Yeah. So our next speaker is Dr. Sougata Mallick, and Dr. Sougata Mallick is currently employed as a postdoctoral researcher at CNRS THALES in France. And prior to that, he did his PhD from Nicer Bhubaneswar, and his expertise is in the area of imaging of magnetic textures, transport measurements, and dynamics of magnetic solitons. And he has also worked as a postdoctoral researcher in University of Paris, France, where he worked on how the Skyrmions can be stabilized at room temperature in the absence of an external magnetic field towards its efficient motion. So without taking much time, I would ask Dr. Sougata to present to share his presentation. So let me just, yeah.
Thank you very much. Am I audible?
Yes.
Okay, and do you see my screen?
Yes, yes.
So thank you very
Just
much
a
for
little
the...
bit raise your voice. That would be better if you can.
Okay.
Yeah, that's
Is
fine.
it better
That's
now?
fine. Yeah, that's fine.
Okay. So thank you very much for the introduction, and let me begin with thanking Professor Muduli to give me a chance to present my work in this workshop. And then the title of my presentation is Stabilization and Motion of Magnetic Skyrmions. So this is basically the work which I have been doing for last 3.5 years during my first postdoc in laboratory physics solid, and now in CNRS THALES. And this work was partly began during the end of my PhD with Professor Subhankar Vedantu in Niger, Bhubaneswar. So the overview of the plan of my presentation would be the following. Naveen has already introduced the topic, so I will not go into detail of the Skyrmion theory, but I will start with a brief know-how about the Skyrmions. And then the main result part are mainly divided into 3 parts, where in the first part I will show you how we can control the Skyrmions in the absence of any magnetic field. And in the next 2 parts, I will consider 2 different ferrimagnetic systems, one with terbium cobalt and another with heterostructure based on ferrimagnet and ferromagnet combination. And I will show you how we can stabilize the skyrmion and drive them in such systems. We cannot go to the next slide. Okay. So as Naveen has already told you, skyrmions are topologically stable spin-swirling particle-like entity. Now, like in a skyrmion, if you go from one side to upspin to continuous rotation to downspin in the center, and you can go to the upspin in the other side, you complete a complete 2 pi rotation. And you map them in a 3D structure, it looks like this. And that is why they can be defined by something which is called the skyrmion number, which is either plus or minus 1, depending on their polarity and winding number. And they are different from the ferromagnetic state, which is shown here, because you cannot go from a continuous rotation of ferromagnetic state to this state without breaking the symmetry. And that is why these textures are topologically protected. But as you know, that normal ferromagnetic exchange supports only the parallel and anti-parallel alignment of the spins. So to introduce a chirality, you need a term which is called the Zylosensky-Moria interaction, which will introduce some chirality. And for this, you need to have some symmetry breaking in your system, and you need to have high spin orbit coupling. And the usual sample structure which we use to have this is put the ferromagnet on top of a heavy metal and then cap it with a different heavy metal to have the structural asymmetry in the vertical direction of the sample. These skyrmions are useful because they are topologically protected, and that is why you can have many emergent electromagnetic phenomena related to its topology. You can also use them in skyrmion-based racetrack and logic memory devices, as Naveen introduced you in the previous talk. Now, in a thin film system, from the experimental perspective, if you write the micromagnetic energy, it takes the form like this, where the first term is coming from the exchange, the second term from anisotropy, and the third term from the DMI. So you can tune all these physical parameters to go to a state where you can have spontaneous textures in the ground state of the system. And how you can do this? If you start from a bubble domain state, you put a certain value of Zylosensky-Moria parameter and anisotropy, and then you see over a certain range of D and K, you can stabilize skyrmions, and also you can have some states where the skyrmion stabilization is not possible. Also, if you go to the spin reorientation transition thickness of the ferromagnetic layer so that your anisotropy is zero, you end up with a hysteresis loop like this, so that in the demagnetized state, you have the stripe domains, and when you apply some magnetic field, you can stabilize the skyrmions. This is a magnetic force microscopy image with the scale bar presented here, so you can see that the skyrmions are really 100 to 200 nanometer in size. Also, you can nucleate them using notches, because here you will have more heating and accumulation, and the current density will be larger in the track. So when you put some current pulses, you can nucleate the skyrmion from these notches, which has also been experimentally realized elsewhere. Now, one important aspect of skyrmions is that they can be driven using the spin torques. And the spin torques, basically what we work on nowadays is the spin orbit torque, which depends on basically two phenomena. One is the spin Hall angle, another is the current density in the heavy metals. Once you put the charge current in the heavy metal, it will introduce a spin current in the ferromagnetic layer, which will move the skyrmions. However, you see, along with the drag force in the longitudinal direction, you will have a Magnus force which is associated with the topology of these skyrmions. So your skyrmions will be deflected towards the edge, which is a problematic situation, and I will try to tell you how we can solve this. So now we can stabilize skyrmion in thin film systems. We can also move them. Now the progress we need to make for it to have a device real life application is stabilizing small skyrmions below 50 nanometer. Improve mobility. Of course, we want to drive them with higher velocity, and most significantly reduce the skyrmion Hall effect, which is deflecting the skyrmions towards the edge of the track. And for this, basically, we need to move towards the antiferromagnetically coupled sublattice systems. However, we all know that the antiferromagnets are insensitive to magnetic fields. So in the first part of my presentation, I will tell you how we can stabilize skyrmion in the absence of any external magnetic field. Now, in a ferromagnetic bilayer, here you see the cross section of the sample structure. So two cobalt layers are separated with a gold layer, and in each side I have heavy metal as platinum. In such a system, the cobalt layers will be dipolarly coupled, and that is why the first term with exchange and anisotropy, the second term and DMI, you will have another additional degree of freedom, which is coming from the domain to domain wall interaction, and basically the dipolar coupling in the system. Now, if you want to stabilize the skyrmion at zero field, what you need to do is you need to increase the domain wall energy significantly, so that the domain wall formation becomes energetically unstable and they can host skyrmions in the absence of any magnetic field. And to do this, basically what you can do is increase the anisotropy energy of the system. Now, in a conventional skyrmionic based ferromagnetic system, when you start working with the spin reorientation transition thickness so that your effective anisotropy is almost equal to zero, in the demagnetized state, you have spontaneous textures. And when you apply some magnetic field, you delete the textures and you stabilize the skyrmions. Now, in our system also, we started with something similar, where we had the vanishing Riemann magnetization state. And you can see here, when we apply 50 millitesla field, we can stabilize the skyrmion. However, as soon as we release the magnetic field, they go back to the stripe phase. That means the system does not have enough anisotropy. And now what we do is we decrease the thickness of this cobalt layer from 1.6 to 1.45 nanometer, and you see from the hysteresis set that now the nucleation field has moved to the other side, giving us almost 100% remanence, and we can stabilize skyrmions in some external magnetic field, and as soon as we release them, the skyrmion texture retains its shape. And this is because it has almost 100% MR. Also, you can see from these minor loops that depending on how much initial saturation field you apply, when you come back, you can achieve different density and size of skyrmions in the zero field stabilized state. Now, we all know that we need to move the skyrmions for their application in real devices. So for this, we took a connection like this, where in one side on the nano track, we have titanium gold point like contacts, and in the other side, we have electrodes, and then we inject current through this. But you see where I showed you in the zero field, I could stabilize skyrmions in the imaging. However, when I put current pulses, they nucleate the textures everywhere. I reduced the thickness further to increase the anisotropy, but still could not go to the skyrmionic state, and they still went back to the stripe phase. And this clearly shows that what was stable for the static measurement is not stable for the dynamic measurements. And that is why we had to reduce the thickness of the cobalt further to have even larger anisotropy. And now you can see that with applying current pulses, we can nucleate the skyrmions and we can move them in the nano track. This is a 3 micron wide track, and the current pulses we put are typically 5 to 10 nanosecond in width. When we take opposite polarity skyrmion, then they move in the other direction. Also, they have the longitudinal motion, which is direct indication of their topology, and it confirms their topological nature. If you want to calculate the velocity, you can plot them with the current density, and we have the skyrmion velocity, which is comparable with the literature reported values. So here I show you that we can successfully stabilize skyrmions in the absence of any magnetic field during both static and dynamic measurements. However, if you see that they are getting topologically deflected, and when they reach the edge of the nanotrack, they are annihilating. So the solution for this is directly associated to my present postdoc, which is why we need the reduced magnetized systems. So in reduced magnetized system, you can see you can have significantly lower switching time because of low angular momentum, and also you can have a low FMR half period time. Now, because of the reduced magnetization, you can have smaller stray fields. So basically, you can go to smaller skyrmion. Because of the antiparallel alignment of the spins, you can have very low net angular momentum, and that is why you can cancel the topological deflection. And they are also protected from the magnetic perturbation because they are strongly antiferromagnetically exchange coupled. Basically, these reduced magnetized system are two in nature. One is synthetic antiferromagnet, another is ferrimagnet. For my postdoc, I have considered only the ferrimagnetic case. And the ferrimagnets has an added advantage over the synthetic antiferromagnets because here you can change the temperature of the alloy or your ferrimagnetic multi-layers to access different magnetic states. So here basically around 200 Kelvin, you see in this diagram, I can have a state where the upspin and downspin moment compensate each other to reach the magnetic compensation. So very small skyrmion size. And here they compensate their angular momentum. So basically you can move the skyrmions without any topological deflection. This is just to show you a cartoon of an antiferromagnetically coupled bilayer system. You can see in top and bottom layer, both the skyrmion moves in a straight line path. So in this case, I have considered two different systems. The first one is terbium cobalt based multi-layer ferrimagnets. So I go to this part, and in the beginning, we started with the terbium cobalt alloy because that is the most popular scenario for the ferrimagnets. People work with alloys, but we realized when we work in the terbium cobalt alloys, when we go towards the compensation temperature, the magnetization reduces, that is good, but the anisotropy becomes so large that it becomes almost impossible to stabilize any skyrmion in this system. Because if you remember the domain wall energy equation, we need lower anisotropy as well. And that is why we decided to work on the multi-layers. So here basically we have cobalt, terbium, platinum repeated 5 times. So essentially what will happen, the cobalt terbium will be antiferromagnetically exchange coupled, and in between two cobalt terbium they will be having the dipolar coupling. The platinum will be in contact with cobalt, so it will provide you the DMI to stabilize the skyrmions. Also, recently there has been a paper published from our group where Fernando has shown that gadolinium and terbium in this range, they can lead to significantly large DMI in such platinum cobalt gadolinium or platinum cobalt terbium based heterostructure. We will measure this soon using BLS to quantify the exact DMI in our system. And also we are now trying to probe the large torque or orbital current contribution which can come from the terbium moments. So in our sample structure, you can see we take platinum cobalt terbium multi-layers where the cobalt thickness is varied between 1 to 1.5 nanometer and the terbium from 0.25 to 1 nanometer. The important thing to note is the monolayer thickness of terbium is 0.35 nanometer. So when you see the HRTM imaging with ETX mapping, you see below the monolayer thickness of terbium, we don't have any well-defined peaks and we have strong intermixing. However, when we go above 0.5 nanometer, the terbium peaks becomes more prominent and we have less intermixing. If you see this in the magnetization curve, this directly give you an indication that there is a strong antiferromagnetic exchange coupling between the cobalt and terbium layers above 0.4 nanometer because the magnetization decreases sharply. And this says that below 0.25 nanometer, because the terbium layer was not continuous, so the antiferromagnetic coupling was not strong enough. And when we measure these samples in MFM, we could stabilize skyrmions. So in the demagnetized state, in conventional room pressure MFM, we could stabilize the stripe. When we applied some external applied magnetic field, we could stabilize the skyrmions. But as soon as we go to this scenario where the antiferromagnetic coupling is strong enough, we cannot measure the textures with conventional MFM anymore. We have to go to the vacuum MFM because of the drop of stray field. And still you can see that we can obtain the spin spiral state. We need to apply some magnetic field and we can stabilize the skyrmions. If we go take further higher in the terbium thickness, the system does not remain out of plane anymore. It goes to in-plane state, and that is why you can see here the in-plane domain walls in the MFM images. And now, because the initial part in these cyan circled areas, it is easier to measure with the conventional MFM. So we prepared nanotracks of these samples and applied some current in it. And in the initial measurement, what we obtained that we have a mixed of skyrmion motion. Some skyrmion are static, and we also see some nucleation and annihilation. Now, if you see this video, it is a 2-micron wide track. You can see the skyrmions are very small. They move. Also, there is a lot of nucleation inside the track. And the reason behind this can be many. One is terbium is highly resistive, and that is why it is accumulating more heat, which is leading to further nucleation. And also, the platinum thickness in our sample is 1 nanometer. And Sachin Krishna will tomorrow show you that below 3 nanometer of platinum thickness, the spin orbit torque effect is not efficient enough. And now that is why in our new samples, we are growing the same series of samples with higher platinum thickness, and we are also trying to improve the torques. But more importantly, what you see here, that we can stabilize the skyrmions with very low size. In fact, I have skyrmions with 30 and 40 nanometer diameter wide, and we can move them using the spin orbit torque. Now, this brings me to my last part of the presentation, where we have stabilized the skyrmion in a heterostructure of ferrimagnet and ferromagnet assembly. So why we chose this topic is because last year, our group collaborated with IJL NOSI, published an work where they show that in a normal heavy metal, if you put the spin charge current, you can have the spin current, which is the normal spin Hall effect. However, if this layer is magnetic and it is in plane magnetized, then the spin current, which will have the direction out of plane, the polarization of the spin current will be partly aligned with the magnetization direction of the magnetic layer. And in this scenario, you will have the combined, in this scenario, you will have the combined
So,
effect of
Sougata,
spin Hall
please
effect.
try to summarize your talk. Yeah.
Okay, so the main message is here you can have the global spin Hall angle coming from both the spin Hall effect, which is significantly larger than the platinum based system, and that is why we tried to use this one as the spin current source now. So we will have an in-plane magnetized gadolinium iron cobalt, and on top of this we put the platinum cobalt copper based heterostructure. So because I have no time, so I will not go into the optimization of the samples, but I can show you from this curve that here I have the gadolinium iron cobalt in plane magnetized, which is saturated around 300 millitesla. And if you zoom in this part, you can see the skyrmionic heterostructure. So in this kind of samples, we can go again from the demagnetized state, and as you apply magnetic field, you can go to the skyrmion stabilization. And here also, you see we have the combined effect of nucleation as well as motion. There are some things we need to do more, like increasing the gadolinium iron thickness, because we want more spin current coming from this particular layer. But already you see with platinum 1 nanometer, if we obtain some motion of the skyrmions, this is coming mainly from the gadolinium iron cobalt layer. So to summarize, we have done the zero field control of skyrmions in ferromagnetic layer, and the implementation of the same concept in synthetic antiferromagnets will be shown to you by Sujit Panigrahi, and also how the skyrmions can be moved in low pinning material will be shown by Brindavan. And we have stabilized very low size skyrmions and driven them with electrical pulses in terbium cobalt based multilayers, and the same for gadolinium iron cobalt and platinum cobalt copper based heterostructure. So I would thank my team members who have worked relentlessly with me for the completion of this project, and thank you all for your attention.
Yeah, thank you, Sougata. Thank for this nice talk. And we have few questions. So one of the question I am reading from this chat box. So Ajit Sahu is asking about the slide 7 regarding this MFM images. So his question is, when using the MFM technique, how do you distinguish magnetic bubble domains and skyrmions?
Okay, this is a nice question. Okay, there are some ways to distinguish magnetic bubbles and skyrmions. The best way to determine to distinguish between them is to apply some current pulses and to check if they are moving with the current pulses or not. This is the best way. If they are magnetic skyrmions, they will move. If they are bubble domains, they will not move. And then also all the samples which I have shown you, I have done the characterization, which I have not shown you the data. They all contain some significant high value of DMI. So we know that there is a specific type of chirality which is already incorporated in the system. So what we stabilize in very low very low anisotropic system with the cobalt thickness close to the reorientation transition thickness, we know that we are stabilizing the skyrmions.
Okay, so the another question is, I think Ravish Kumar Raj wants to ask
Yes, sir.
one
Yes, sir.
question. So
Yes.
Ravish, yeah, you can please ask the question.
Yeah. Hello, sir.
Hello.
I want to know that when we apply current in a heavy metal, so due to associate they are derive the ascormion. But we are wondering about that when we apply a current in simple heavy metal, one case, and another case when we apply current and drive the ascormion, the resistivity of the heavy metal will affect while driving the skyrmion or remain same, sir? That means resistance.
Okay, this is quite
Because
difficult to tell. Okay,
ascormion will giving the adverse effect the electrons which is directly coupled with the heavy metal. So I think may affect due to interaction of electron with the skyrmion. So I think it will how effect and so I want to know, sir.
okay. The direct answer of this question is like I don't check the resistance of my track during I am doing the measurement, so I cannot really comment if it is changing the resistivity of the total stack or the heavy metal or not. But what I can tell you is like I always check the resistance of my track after applying one pulse just to check if it has damaged my track or not, and the resistance usually remains constant. So in the equilibrium state, after we apply the pulse or after we take the measurement, I can tell you that the resistance does not vary significantly.
Okay, okay, okay.
So Professor Mudli has already
Yeah,
raised his hand. So yeah.
I was wondering, I had a technical question because you are doing this MFM. Maybe you know what kind of tip you use to image this? Is there any specific like low
Okay.
coercivity or high movement or something that you can give us some idea?
This is a very important question, Mudli sir. Actually, it depends on which system you are working on. Like if you are working with the like ferromagnetic samples, you can use a conventional soft magnetic tip. Like you can take 7 to 10 nanometer of cobalt capping with a capping layer of 20 nanometer of aluminum or something. When you are working with synthetic antiferromagnets, because you know that they are the exchange coupling between the two lattices is so large that you cannot part up those textures, so you can basically take a very high moment magnetic tip. So what we do usually, we take a 40 nanometer or 50 nanometer thick cobalt tips. However, the system I work on the ferrimagnets, because they are very amorphous and I expect that they are very low pinned material, so I need to go to a tip thickness which is very low in magnetization. So the tips which I have used for this study, they are like 5 nanometer cobalt iron boron capped with 30 nanometer aluminum. So it depends on which system you are working. We calibrate the tips before starting a new system every time.
So you prepare your own tip or?
Yes, we prepare our own tips.
Okay, okay.
We buy the AFM tips and then do the magnetic coating ourselves.
Coating, you do the coating in your sputtering system?
Sputtering, yes, sputtering.
Oh, okay, okay, okay. Interesting.
So we can have one more last question from Arjun. Yeah, Arjun.
Yeah, like it was a nice talk. I just wanted to ask a thing like about the DMI that you have told that your system is having very high DMI. So how you have measured and what is the magnitude of the DMI that you are having in your system?
Okay, I told you that I expect that my system has very large DMI because the
Okay.
DMI I have not measured yet. I will measure, but to answer your question, DMI can be measured by BLS. So in this particular sample, I have not measured for say the
Sorry,
first part of
voice
my
is breaking.
presentation,
Okay.
the platinum, cobalt, gold. I have measured the DMI using BLS.
And also, like you have shown that the pulse width of the pulse you are using is up to 5 nanoseconds. So, what is the rise time and fall time of the signals that you are using? I mean, the
Yeah,
generator,
so
pulse
that
generator.
the rise time was around 600 picosecond.
Okay, so with 300 picosecond, 600 picoseconds, you are able to stabilize square pulse of 5 nanoseconds.
When we apply 5 nanosecond pulse, usually when we recalculate the pulse shape, like we shape the image, and when we recalculate it gives like 4 to 4.2 nanosecond of the peak, and then the rest of the thing
So
is
it is square.
it is square up to half width at full maximum.
Okay,
It's
okay,
not like exact square, but we always consider the half full width at half maximum.
okay,
There it is square.
okay, fine, fine. Thank you.
So, well, there are few other questions also, but since we are, I think, getting late in this session, so I would request other people to ask questions in the chat box. Maybe Sougata can respond to these questions. So,